So let's see one more problem called dining philosopher problem. We'll try to write the solution of this particular dining philosopher problem using semaphore. Okay. Now what is the concept of this particular dining semaphore? Okay. So in some particular organization or company, there are five philosophers are there. So then I will give the name as P0, P1, P2, P3, P4. Okay, so their duty is to think, and after thinking they need to write some work. Okay, they need to write and submit their work during this part, and they are sitting in a round table. They are sitting in a round table. Okay, the problem with these philosophers is they don't interact with each other. Okay, they don't interact with each other. Okay, the problem or condition is that they don't interact with each other. Okay, and in between this particular, in the middle of this particular table, there is a rice bowl. Okay, there is a rice bowl. Whenever these philosophers gets hungry, because all the philosophers are thinking. Okay, so at some particular point of time they felt hungry. Okay, they felt hungry, and whenever they are hungry, they will take this particular rice from the rice bowl. Okay, and put it on the table, and they will eat it by using two chopsticks. Okay, by using two chopsticks. I will name this particular chopsticks C0, C1, C2, C3, C4. Okay, so there is a condition that each philosopher, whenever they will get hungry, first they will pick up their left chopstick and followed by right chopstick, because they cannot pick both the chopsticks at the same time. Okay, so they will pick first left chopstick, then right chopstick. Okay, now the left chopstick, let's take P0. The left chopstick will become C0, right chopstick will become C1. Okay, for P1, if you take this one, there will be a cycle. So left chopstick, he has to eat first. He will pick up C1 and C2. Then for P2, he needs to pick up C2, C3. Okay. Similarly, for P3, he needs to pick up C3 and C4. And P4, he needs to pick up C4 and C0. Okay. That means if a process Pi, okay, I value ranging from 0, 1, 2, 3, 4. Okay. So Pi has to pick up, then he needs to pick up chopstick I and as well as chopstick I plus 1. Okay, so this is a circular table. This is a circular table. Okay, if you take this particular chopstick, okay, how many chopsticks are there? Five chopsticks are there. I will take five chopsticks. Okay, 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So if these all are initially available, all are initially available. So what I will do, chopstick of I equal to 1. All are available. So chopstick of I equal to 1. So when P0 wants to eat, okay, what he will do? He needs to take chopstick 0 as well as chopstick 1. So this will be turned into 0. They will be turned into 0, so that P1 doesn't have C1, so P1 does not able to eat. P4 doesn't have 0, C0, chopstick 0, because it is not available, because P0 is eating, so it is not available. So P4 cannot able to eat. But C2, P2 tries to eat, he can eat C2 and C3. He can eat with using chopsticks C2 and C3. So P0 has to eat. What are the chopsticks he needed? C0 and C1. So Pi wants to eat. Okay, he needs chopstick Ci and chopstick Ci plus 1. Okay, so it is a circular table. When P4 comes to it, he needs C4 and Ci plus 1 will become C5, but it is a circular, so it will become modulo 5. There are 5, so it will become 0, C4 and C0. Now let's see the implementation of this particular thing. Okay, so what it will do, first we will initialize a chopstick array with semaphore. Okay, so all of them are initially, so all of them are initially 1. Okay, they are assigned to 1 chopsticks, they are assigned to 1. Now if, as we have seen, if P0 has to eat, it needs chopsticks C0 and C1. So now look at here, weight of C0, okay, and weight of C1, 0 plus 1, 1, so it will be C1, okay, weight of C0 and C1. So C0, C1 are taken by P0, okay. So after getting two chopsticks, P0 will eat. Once he finishes eating, he will release this particular C0 as well as C1, okay, C0 and C1, signal on C0 and signal on C1 will be done. Again he will come to, he will go to his work and think, okay, he will do thinking, okay. So this is a continuous process. Any process that has to execute, that will do this one. Similarly, if P1 has to eat, P1 needs, okay, P1 performs wait on C1 and wait on C2, okay. Then he will eat. So eating here is critical section. Then he will release C1 and release C2, okay, S on C1 and S on C2. Similarly, if it comes to P4, okay, now let's see P4. P4 needs chopstick 4. So wait on C4 as well as chopstick 0. But the code here is 4 plus 1, 5, 5 modulo 5, 0. Okay, so that's how it will get C0. Then he will eat and again he will release signal of C4 as well as signal of 4 plus 1, 5 modulo 5. Okay, so it will be C0. So this code looks sufficient for the above dining philosopher, okay. But this is not the problem. The problem comes when all the philosophers are hungry at the same time. All the philosophers are hungry at the same time. This is a problem, okay. When all the philosophers are hungry at the same time, okay, they try to execute this particular code. That means when, so let's go to previous slide. When all the philosophers are hungry at the same time, there is a problem. So what is the problem here? So in the problem, the philosopher C0, okay, the philosopher C0 is sorry, P0 is picking the chopstick C0, okay, because he has to pick left chopstick, then right chopstick. So at the same time, P1 is picking C1, P2 has picked C2, P3 has picked C3, P4 has picked C4. Okay, the problem here is all the philosophers, because they don't interact with each other, they pick their left chopstick on the left hand with the left hand, okay, and right chopstick has been taken by the next philosopher, okay. So all of them has left one chopstick on one hand and there is no next chopstick, that is right chopstick is available here. So what will happen when this code, when this particular code has been taken concurrently, okay. So let's see this one. In this particular code you can see that first in the round robin fashion, okay, the time counter, this P0 is picking C0, so it will become 0. P1 is picking C1, so this will become 0. P2 is picking C2, 0. P3 and P4, all of them has been taken after completing P0, P1, P2, P3, P4. Then it will be turn P0 and try to execute wait on C1. Now look at wait on C1, it is not available, okay. Then it will continue to execute on the while loop, okay. Then after that P0 will go and execute C2. C2 is also not available. P2 executes C3, try to pick up the next chopstick, it is also not available. It is a P4 try to execute, P3 try to execute PC4, not available. P4 tries to execute C0, not available, okay. So what will be happen when all the philosophers are get hungry and try to execute this particular code and pick up the next chopstick? Look at here, the chopsticks are not available, okay. The chopsticks are not available and there is a condition that you need to pick up both chopsticks so that you can eat, and no one is ready to put down that particular chopstick, okay. No one is ready to put on that particular chopstick, okay. This problem comes because you are incorrectly using this particular weight functions, and you are using this particular weight functions in a circular manner, that will leads to a problem called deadlocks. Okay, that will leads to a problem called deadlocks. Incorrect usage of semaphores will leads to a deadlock. Okay, right. So the problem here is this code, this implementation does not give you a proper solution to dining philosopher problem. Okay, because we used incorrectly the incorrect use of semaphores. Okay, so we cannot use this particular code to implement solution for to provide solution for critical section problem that is caused with deadlocks, sorry, dining philosopher solution. But what are the possible remedies that we don't get, we use the same solution but we don't get deadlock? Okay, that means whenever all are hungry there should be a deadlock. Okay, so this solution provides when p0 is executing, okay, we can only allow either one or maximum of two philosophers to eat. Okay, that means if p0 is eating, he can take c0 and c1, and p0 and p4 they cannot eat. Okay, so the only options are either p2 will eat or p3 will eat. Okay, so if we allow p2 eat, he will take c2 and c3. Okay, then he will take c2 and c3, so that p3 cannot have c3 and p1 cannot have c2. So maximum at a time they can be only two philosophers they can eat. Okay, we can allow only two philosophers can eat. Otherwise, we'll provide one more chopstick, but that will not be a better option. Okay, if we provide one more chopstick, maybe we can avoid that particular deadlock, but we cannot take that. Otherwise, there is one more asymmetric solution, that we let odd number philosophers to pick up her philosopher pick up her left chopstick and then right chopstick, whereas even number philosophers to pick up her right chopstick then left chopstick. We can avoid this particular deadlock problem. But anyway, this particular semaphore solution does not provide the proper solution to dining philosopher problem. So we need to go for one more, that is monitors.